Hello, fellow pedestrians. In this lecture, we're going to examine the symmetries that are provided by some differential equations and how we can take advantage of certain symmetries that are exhibited in these DEs and provide us with guidance to be able to reduce the order of the differential equation, going from the second order differential equations to first order differential equations. So let's start firstly with something called shifting symmetry of y, so of the function we are searching for every time. Now, what is shifting symmetry? Shifting symmetry is taking y and taking to y plus something, plus a. And this is the most trivial symmetry there is. It involves having, let's say, function where y prime is there, is present, also y prime is present, x is present, but y itself is not there, so that is why, under this symmetry, this remains invariant, meaning that whenever you find a differential equation of second order and y is missing, you can deploy the transformation y is equal to u of x, and you will have your equation reduced to first order. That's it. This is the most trivial example, the most trivial symmetry of differential equations that the differential equation can exhibit. And doing this transformation, you immediately get that this is reduced to first order. And many times this is so much easier to solve. Now, secondly, we have scaling symmetry of y. Now, scaling symmetry is again taking y and have it multiply by a constant, let's say, call it lambda. Okay, and let's exhibit some examples to be able to see what we are talking about. Let's say you have y prime prime plus py prime plus q, this qy is equal to 0, and y and its derivatives in its term are present only once. So this is order 1 of homogeneity. Homogeneity. Let's say you have plus a y squared plus b y prime is equal to 0. So y derivatives here is of second order. Another example can be, let's say, y squared, y prime plus, I don't know, a, y prime prime plus b, y prime to the third is equal to 0. This is third order of homogeneity, and so on and so forth, right? So if the order of homogeneity is preserved in its term of the equation, then there is a scaling symmetry because each time L presents itself, it's going to cancel out from its term, right? And if you have this kind of equations, then a way to guess its solution, like we have done in the constant coefficients in the previous lecture, where we had y is equal to r of x, we can generalize now, um, since this would be the last case we've seen, but these were constant. So a generalization where you can drop, uh, let's say, constants or just functions from each term could be e, the function of x, right? Um, and as you can see, this change of variable u of x is just ln of y. So indeed, if you send y to ly, then u will be sent to a constant plus ln of y, which is just u. So what we are doing here, we are starting and developing, and talking about some shifting symmetry. And then we're talking about some scaling symmetry of, let's say, the same variable. By a change of variable, in this case, this is a change of variable, we transform our current scaling symmetry to a shifting symmetry of, of the newly founded variable, right? So when we employ this variable in our equation, if this equation holds, then what we have done is transformed the equation into this form. So we went from scaling symmetry of y to the shifting symmetry of y by this transformation. We will see that there is a similar case when we are going to talk about the shifting symmetry of x and the scaling symmetry of x. So indeed, by having this transformation here, we are moving into having a shifting symmetry of u of x in the new transformed differential equation. Um, so we are really bringing us to the previous trivial case, right? So the full transformation we are going to use, and I will encapsulate them in red. This is y, meaning that y prime is just u prime e to the u, and y prime prime is equal to u prime prime plus u prime squared e to the u. This is all the transformation we need when we find a differential equation that exhibits this scaling symmetry. And let's examine an example right away. So let's say we have y prime prime is equal to y prime squared plus y prime. Now, there's two y's here, two y's here, two y's here. Doesn't matter that they're derivatives. Think of it that each one provides with a lambda when there is a scaling of y. So lambda squared is going to get dropped from its term, right? So we are indeed in the case of the scaling symmetry of y in this differential equation. We are going to use these transformations here, meaning what we are going to get is this and this, so this guy and this guy, it's e to the 2u, u prime prime plus u prime squared is equal to u prime squared e to the 2u plus e to the 2u, u, right? And now, indeed, this, and this goes away, and that leaves us, this also cancels with this, u prime prime is equal to u prime. And like we promised, we are indeed uh, we indeed have a differential equation that has a shifting symmetry of the new variable. You see, there is no u here. There's only u prime and u prime. So again, so indeed it lies in the previous case of shifting symmetry. So again, taking a change of variable, meaning that this is v, this is u. So v prime equals v, meaning that the value x equals v, or v is just say e to the x, or u is just the 1 e to the x plus another constant, and finally y is equal constant e to the k e of x, right? We are going backwards. So we first found what v is, v of x, then we integrate this to find u, so u is the integral of this, which is this, and finally y is this guy, is e to this guy, right? And as you can see, this is indeed invariant under the transformation we began with, meaning that if you send this to a constant time this is going to change about the constant, which is the same solution regarding when we're talking about linear. It's a linear dependent solution, so it is considered the same solution, right? Now, next on the list is the shifting symmetry of x with respect to x, right? Now, um, imagine that you go ahead and take the derivatives and see how they're transformed. What is shifting symmetry? So again, it's taking this and adding something, right? Now, how the derivatives of y, the function in question, are going to behave under this shifting symmetry of x? They're going to be unchanged. They're, so you can easily check that. So this is just the x of a dx, right? And this just 1. So this is equal to this, meaning that the only thing that's going to be relevant is x itself. So the general equations that exhibit shifting symmetry with respect to x is of this form, where there is no explicit dependence on x. So if you find a differential equation where x is missing, then you can immediately say that there is a shifting symmetry with respect to x, because nothing else is going to change if you send x to x plus something, right? This kind of equations are also called autonomous, and it's a term that is borrowed from physics, where you have cases of dynamic equations that does not explicitly, let's say, depend on time, where because time is a dependent variable, most often in physics. And you can have the time evolution is regulated internally, etc., and so on and so forth. Now, the general idea when you have a shifting symmetry with respect to x is to interchange the roles of dependent and independent variables of x and y. So let's say we interchange x and y, meaning that we are going to search for solutions of this form. So x is equal to x of y, where now y is the independent variable and x is the dependent one. And x is now the unknown equation to find in order for the shifting symmetry of the old independent variable to be a shifting symmetry of the new, let's say, function. Now, what this means is one can write that y is known to be dx dy dx, or it can be written as 1 over dx over dy. And we can denote this, for saving space, as x dot, where dot is going to mean for us that we differentiate with respect to y. Okay, now y prime prime is going to be ddx of this guy, right? Or dy, since we're talking about functions of y now, 1 over x dot dy dx. But this is nothing more than this guy, so we have the differentiation of this with respect to y, 1 over x dot dot, and this again 1 over x dot. So we see that this term keeps popping and keeps popping. Now we can go ahead and set this. We said that this is just a function of y, since the new founded let's say function, the new dependent variable is x. So setting this to u, let's say you set this to u of y, so this is just u dot and u, right? So the only transformation that is needed here, and I'm going to rewrite them, not a dot, y prime is equal to u of y, and prime prime is u dot u. So when a differential equation exhibits a shifting symmetry with respect to x, or differently put, if there is a differential equation where x is not there explicitly, then you can immediately use this kind of transformations, right? And you can easily see that this equation, where x was missing, can be immediately transformed to u equals to 1 over u of u y, right? And what is this? This is just the first order differential equation with respect to y. And we already know how to solve it. Now let's take an example, and we'll always uh, get this. So let's say you have y prime prime is equal to y prime squared. One could also wonder that some examples we are doing have other kinds of symmetry that we already talked about. Yes, this is very true. Symmetries are generally not bound to a specific function. But what I mean is that the differential equation may exhibit a lot of symmetries, more than one, and it is we need to decide what symmetry we are going to use each time and deliver the result. Now, let's say we have this differential equation, and we're going to use these transformations. So y, this is u dot u is equal to y prime squared. This is u squared. So this and this goes away, meaning that u dot is mu over y. And what is u dot? The u dy is a function of y. I'm going to tell it again. Is equal to u over y. This is just a separable question, separable differential equation, the easiest kind. So you have du is equal to dyy, meaning that y, or sorry, u is equal to a constant times y. And this is u, right? So to find y, we're just going to integrate with respect to x, because this is x differentiated. So this is written as this is y prime, so dy dx is the y, or ln dy y is a constant dx, meaning that ln of y is just the 1 x plus 2, or y is just another constant e to the ax, right? Nice. Again, you can easily see that this equation that we found is invariant indeed under the shifting of x. So it is invariant under x goes to x plus a, because it's going to add a term here, imagine, which will get in front of here. It's going to be lowered down as a constant. So what that tells us is um, the only thing that matters in autonomous equations are the initial conditions to find the constants, and then you're all set. Now, lastly, we have the scaling symmetry with respect to x, which again is just x goes to lambda of x. Now, let's see how everything behaves under this transformation. Of course, only x is scaling right now, so it's going to remain unchanged. The first derivative, however, which is dy over d to the lambda of x now, is nothing more than lambda to the minus 1 y prime, right? Meaning that this transforms like gives a minus power of lambda. Exactly the same way, this gives minus 2 powers. So to check if a differential equation exhibits a scaling symmetry with respect to x, we go ahead and check its term, right? To give you an example, let's say we have x y prime prime plus y prime plus 1 over x y is equal to 0. Now this gives you plus 1 because this is 1. This guy gives you minus 2. So from this term you get minus 1. This is minus 1. This again is x to the minus 1, so minus 1, and this is plus 0. So minus 1, minus 1, minus 1, each term has the same order of lambda, right? So this differential equation does indeed exhibit a scaling symmetry with respect to x. Now, we're going to need a variable change. Remember before when we were talking about the scaling symmetry with respect to y, what we did was we chose a variable change where we could go back and use the shifting symmetry with respect to y. This is exactly what we're going to do here. So we're going to need a variable, whereas before we'll have the scaling symmetry to become a shifting symmetry. and we're going to use x is equal to e to the t, let's say, meaning that t is just ln of x, where for x scaling, then indeed this is shifting, right? And now we can use the shifting symmetry from before. What we have before, we have u of y was dy dx. But now our changed variable is t, so dy dt. That's it. So this is written as dy dx, dx dt, which is nothing more, it's just x. You go ahead and differentiate with respect to t, you get the same. So this is just x, y prime. This is y prime, and this, meaning that y prime is just u y over x, and y prime prime is u prime x minus u over x squared is equal to 1 over x squared du dx, which is this guy here, and x minus u. I just rewritten it. And this is equal to 1 over x squared, but this u, as we said, is a function of y. So we differentiate with respect to y minus u, and finally du dy, you can denote it as dot, doesn't matter. Dy dx times x is this guy here, right? So it's just u minus u, and that's it. So the transformations, to sum it up, we're using is this one, and the second one is this one for y prime. And we are indeed going to get from a scaling symmetry to a shifting symmetry. Right, let us take an example. Let's say you have x, y prime prime, y prime plus y prime squared plus 1 over x squared y is equal to 0. Now, firstly, what we're going to do is again check if there is indeed a scaling symmetry with respect to x. So this is plus 1, this is minus 2, this is minus 1, so minus 2 from this term. This term is minus 1 squared, so minus 2, and this is minus 2 plus 0. So indeed, there is a scaling symmetry. And we go ahead and deliver everything we written here. So we have x times this guy, so 1 over x squared u dot u minus u, what is it, times this guy, which is u over x, plus this squared plus 1 over x squared y is equal to 0. So every x goes away, and you have u dot u squared minus u squared plus u squared plus y is equal to 0. This and this goes away, and what you're left with is just a separable first order equation, right? Because this is du dy, as we said, and is equal to minus y over u squared, or u squared du plus y y is equal to 0, and we'll get an implicit form of solution. It's going to be e to the third over 3 plus y squared over 2 is equal to a constant as a solution. And finally, y is just u over x, meaning that x of y, because as we said, now x is a function, can be written as e to the y over u, which we can leave it at this form because this is a non-trivial integral, and this is pretty much how we deal with those kinds of symmetries in general. Now, what we're going to do now is try to engage in some examples of differential equations, where firstly we need to find what symmetries they exhibit in the first place and choose what is our cup of tea to use. So let's say we have 1 plus x squared y prime prime plus 2xy prime is equal to 1. Now, we can already see that y is not explicitly here, so we can say that there is a shifting symmetry we can use, and also we have 1y here, 1y here, so there is also a scaling symmetry of y. And let's choose the simplest one, the most trivial one, where we are going to set u is equals to y prime. So this is going to be written and divided with 1 plus x squared, u prime plus 2x over 1 plus x squared. U is 1 over 1 plus x squared. And this is just the linear differential equation of first order that we saw many lectures ago. And we know exactly how to solve it. U naught is equal to e to the minus p, which is this. So 2x over 1 plus x squared dx, which is equal to a constant e to the minus ln 1 plus x squared, which is nothing more than x over 1 plus x squared. Now, u is u naught, which is over 1 plus x squared, integral of rx, this is rx, 1 over plus x squared, over over plus x squared dx. So finally, we get x, this goes away, this goes away, so also this goes away, right? So you only get a constant, so x plus a constant over this guy. And finally, y is just the integral with respect to x of what we found. So x over 1 plus squared plus a constant over 1 plus x squared dx. And this is just 1/2 ln the logarithm 1 squared plus a constant times the integral of this, and this is the arctangent. So let's say the arctan of x plus another constant. And this is the solution, where we chose shifting symmetry of y. Now another example. Let's say we have y prime minus y prime squared is equal to 0. Now here, sorry, this is 2 primes. You have scaling symmetry, y, because there's 2 y's here and 2 y's here. So order 2 of homogeneity with respect to y's and its derivatives. There is also a shifting symmetry with respect to x because there is no x, and there is also a scaling symmetry of x. Why? Because this is 0, this is minus 2, and this is also minus 2. And again, the simplest one to choose is this, where, as we said, the transformation is just y is equal to e to a function of x. So y prime is u prime e to the u, and y prime prime is e to the u prime prime plus u prime squared. And go ahead and plug this here. What we're going to get is e to the u, to the 2u, sorry, u prime prime plus u prime squared minus this guy squared, so e to the 2u prime squared is equal to 0. This goes away, and also this cancels, meaning that the second derivative of u is 0, or first derivative is just a constant, or u is just this guy here, meaning that y is nothing more than a constant times another e to the another constant of x, right? Of course, you could use any of these to prove your point. I mean, you could also use this. So if you want to check the second solution, how it would look like and how involved it would get, using the transformations that we've seen that works for the scaling symmetry of x, this is going to transform, this is y, this is going to be written as 1 over x squared u dot u minus u minus u squared over x squared equals to 0. This is written as y u dot minus 1 minus u squared equals to 0. This goes away, and again we get ourselves a first order linear differential equation with respect to y again, because what we're using when we are using the symmetries of x, you're always going to solve an equation, a differential equation, where y is the independent variable. So, as known, u naught is e to the minus dy over y because of this. So e to the ln of y plus a constant, or just a constant times y, meaning that u is u naught cy. There's no rx is just 1, so dy over u naught. This goes away, so y times ln y plus another constant. But u is just the derivative of y with respect to x, meaning that dy dx is y ln of y plus a constant. So if we differentiate this, we get dy over y ln y plus a constant is equal to dx, meaning that this is ln of constant is equal to x plus another constant. And finally, ln of y plus a constant is just another constant e to the x. And you will get exactly the same with different constants. It doesn't really matter, right? Which is exactly the same solution we found by using this kind of symmetry, right? Now, let's move on to another example. Let's say we have x, y prime prime minus x, y prime squared, y prime is equal to 0. So, um, you can check there is no x missing, so there is no shifting symmetry, but there is a scaling symmetry of x. This is plus 1, this is 0, and this is minus 2, so this is minus 1. This is 1, and this is minus 1 squared, so 1 minus 2, again minus 1, and this is 0, this is minus 1. Indeed, there is scaling symmetry of x. And as far as y goes, there is also scaling symmetry of y. Why? Because there is two terms of y here, two terms of y here, and likewise. Like we already know, we are not going to write it every time, so let's go and plug everything using this kind of symmetry. So x times u prime prime plus u prime squared, and I already dropped the e to the u terms, minus x u prime squared minus prime is equal to 0, and this is written as x u prime prime is equal to u prime. Now, what we have here is a differential equation that again exhibits a symmetry. And so we can, and it's also a second order differential equation. What symmetry is this? Is the most trivial one, which is of this kind, u plus something. So using, let's say, v to be u, then you have x of v prime is equal to v, meaning that the v over v is dx over x. So v of x is x times a constant, and u, which is u prime, is du over dx, is equal to v, which we found, meaning that u is the integral of this, so it's just constant squared plus another constant. Or finally, the solution is going to be e to this. So e to c1 x squared plus 2. Or if you rewrite it, the constant times e c1 x squared. Right? Now, another example. What we have here is 2y y prime plus y prime squared plus y prime to the fourth is equal to 0. The only symmetry that's exhibited here is the one that with the x missing. And this is the symmetry with respect to x when x is shifted. So the transformations for this is you go ahead, and this is nothing more than the u dot u, where again u is a function of y, plus u dot plus e to the fourth is equal to 0. And this is nothing more than dy du dy is equal to minus u times u squared plus 1, which is a separable equation. So the u over u squared plus 1 is equal to minus 1 half dy over y. And like we said in some previous lectures ago, to analyze this, you have u squared plus 1. So you have one real root, which is 0. So a over u plus, and this is now a complex root of multiplicity 1. So the denominator is going to be written as the u plus another constant over u squared plus 1. And if you solve this equation, you're going to get that a is equal to 1, b is equal to minus 1, and c is equal to 0. Meaning that this integral can be rewritten as a of u, so 1 over u, minus, because this is minus, u over u squared plus 1. The u is equal to 1 half. This is just ln of y plus a constant. So this is written as ln of u over square root u squared minus plus 1 is equal to ln of 1 over square root of y, because this goes here and this is the square root and etc., plus a constant, and u over square root of u squared plus 1 is equal to a constant, and squaring everything. This is just some tedious calculations here. U squared over 1 minus over y is equal to s over y again. And u squared is equal to c over y over 1 minus c over y, or just a constant, and multiply both numerator and denominator, y minus c. Meaning that finally this is constant over square root of y minus c. And we're not done. Dy dx is a plus minus of this guy. So integral of square root of y minus c dy is plus minus square root of c integral dx, and this is just 2/3 y minus c to the 3 over 2 is equal to plus minus square root of c x plus another constant. And if you do all these calculations, as you're going to get is that y is equal to plus minus 2/3 to the 2/3, a constant, and x plus 2 to the 2/3 plus another constant. And this is going to be the solution to this differential equation. You can go ahead and plug it if you want, just to have some fun. Now, another example. We are not getting enough. Y prime prime minus y prime squared plus y squared is equal to 0. no x, so we have a shifting symmetry of x. And also we have the same order of y, so again, a scaling symmetry of y, lambda y. We're going to choose y again. It tends to make our lives easier. So we're going to go ahead and plug everything in. So we get u prime prime plus u prime squared for this, and this will go away, plus this would get us u prime squared, and this is just plus 1, right? And this is equal to 0. So u prime, this also cancels, it's just minus dx, right? Meaning that prime is just minus x plus a constant, or u is just minus x squared over 2 plus x plus a constant plus another constant. And finally, the function we are seeking is some constant e to the minus x squared over 2 plus x. So, another example. X y prime prime plus y prime plus x squared y prime to the third is equal to 0. This exhibits a shifting symmetry of y. Why? Because there is no explicit presence of y itself. And also there is also a scaling of x, because this is 1 and this is minus 2, this is minus 1, this is minus 1, this is 2 minus 3, this is minus 1, so again there is a scaling of x. And you can go ahead and choose whichever thing you like, and it will get you to the same example. Now we're not going to do this over and over again. I'm going to just give you the solution and do it yourself. Y is going to be square root of 2 ln of x plus a constant plus another constant. And you can easily see that all these examples exhibit the symmetries that are promised, meaning that this solution does indeed exhibit such kind of symmetry, or such kind of a symmetry, because they're inherited from the original differential equation. Now let us write some more examples with their solutions for educational purposes. Plus y prime minus x y prime squared is equal to 0. This only has one symmetry, which is x lambda x, the scaling of x, and its solution is going to be with respect to y as independent variable is e to the minus the integral of e to the minus y squared over 2 dy. And this is a non-trivial integral, so no need to solve it. Another example is y prime prime is equal to y prime squared. This has a lot of symmetries, doesn't matter which you choose. The solution is going to be e to the k e to the x. And I want to end this long video with a final note on these symmetries. Now, except of having these independent symmetries, you can have also two symmetries mixed together in a differential equation. And it's are usually in this form, where you have x going to lambda x and y going to lambda nu y. Now, the way to solve this kind of differential equations when stumbled across them is you try to create and you try to add a new variable which is dimensionless, and by dimensionless I mean dimensionless with respect to lambda, right? So if you have something like uh, nu is equal to -1, so you're going to have a dimensionless variable which is going to be x times y. You understand why? This is the reason, because this is -1, and with this there will be dimensionless in each of term of the equation. Now again, if n is equal to 1, then you would have that u could be written as y over x, which is again dimensionless. If n was equal to 2, then u could be written as y over x squared, etc., etc. And of course, you can construct many terms that are going to be dimensionless. Another term here would be y prime over x or y prime prime. Now, as a general conclusion to all of this talking about the dimension is the theorem that says that every differential equation that has as many as independent continuous symmetries as its order, then it's always integrable, meaning that its solution can always be written in the sense of integrals on the specific functions of the equation, right? So you can always solve or get a final integral when let's say we're talking about the second order equation, and you find that it has two independent symmetries, so not this kind of symmetries which are mixed uh, together in a single differential equation. Let's say, so this differential equation is of the second order, and it exhibits two kinds of symmetry independently. They both, if you take these transformations and put them here, this will remain unchanged, right? So, because there are two and the order of the differential equation is also two, then this is always solvable, right? And now let's add things by solving one last example where a mixed symmetry is present. Okay, now let's say you have x y prime prime is equal to y prime minus y over x plus y prime minus y over x squared. Now, to find, to check if this is an mixed symmetry, well, of course, you can see that there is no other symmetry here. So, this is for sure 1 from x is supposed to be an x, minus 2 from this, plus n. And this is going to be 0. So, nu here is just 1, meaning that we got this transformation, right? So, if you go ahead and write y as ux, you're going to have y prime is equal to u plus xu prime, and y prime prime is 2u prime plus x u prime prime, and y prime minus y over x is equal to u prime x u prime minus u. This is just x u prime. And now everything is going to written. Now this, sorry, plus x squared u prime prime is equal to x u prime plus x squared u squared u prime prime plus x u prime is equal to x u prime squared. And again, we have a symmetry like that. And we go ahead and say v is equal to u. So this is written like this, which is separable. And finally, u is just 1 over, no, sorry, this was supposed to be v, my bad. Hence, if you solve this, you'll get x times a constant minus ln of x, meaning that u is minus ln of x minus 1 plus another constant. And finally, the solution we are looking for is minus ln of x plus minus, sorry, plus the 2 of x. And this pretty much sums it up for the symmetries that reign through the differential equations. And like we said, remember that when you have two independent symmetries found for a second order differential equation, then the differential equation is solvable. It's always integrable, and you will always be able to write it sorry, in way that ends in integral. Doesn't matter if it's a trivial or not solvable integral, but the differential equation is always solvable. So that's pretty much it. And thank you all for taking all this time and making it up until here. So thank you all, and see you in the next video.